In this video, we're going to apply Avogadro's law to help us see how we can use the volume of gases in stoichiometry calculations for gaseous reactions happening at constant temperature and pressure. Recall that Avogadro's law tells us that at constant temperature and pressure, the volume of a gas is directly proportional to its numbers of moles. This means we can use volume as a stand-in for number of moles of gas under situations where a reaction is occurring at constant temperature and pressure. Let's see how this works. So let's imagine, for example, that we were running a reaction at constant temperature and pressure, for example, by combining gases inside balloons to keep the pressure at 1 atmosphere in a temperature-controlled room. Under these conditions, what we call one volume of an ideal gas refers to a specific and fixed number of moles depending on the temperature and pressure. This means that we can combine, for example, one volume of gas with 3 molecules of a different gas, and this corresponds to a 1 to 3 mole ratio of the two gases in question. So consider the reaction here between 1 mole of N2 gas and 3 moles of H2 gas to produce 2 moles of NH3 gas. And the picture above shows you balloons containing the volumes of gas that we're combining and the volume of gas that we would get out of this. So for example, we've got some volume of nitrogen gas. We've got 3 times that volume of hydrogen gas, and this produces 2 times that volume of NH3. Notice that those volumes correspond to the stoichiometric coefficients in the balanced equation and the numbers of moles that combine. This is a direct consequence of Avogadro's law. So for example, the volume of N2 corresponds to a certain number of moles. 3 times that volume corresponds to 3 times the number of moles of H2, and 2 times that volume corresponds to 2 times the number of moles for NH3. So the volumes relate directly to the numbers of moles, and in stoichiometric terms, we can think about combining volumes of gas, quote unquote, instead of combining certain numbers of moles. It allows volume to be used to count molecules in a sense. Keep in mind, though, as a last caveat, that this is only valid for reactions occurring at constant temperature and pressure, since volume and number of moles get all out of whack if the temperature and pressure are allowed to vary. Let's work this quick practice problem. We're asked what volume of O2 oxygen gas at 25 degrees C and 760 torr, or millimeters of mercury, is required to react with 2.7 liters of propane under the same temperature and pressure conditions. So what we're looking at here is a constant temperature and pressure situation, and we're asking about volumes. We're wondering about volumes. This suggests that we can engage Avogadro's law in what we just saw. We're going to assume that the propane undergoes complete combustion. The reaction goes to completion, and I've gone ahead and written out the balanced chemical equation for this process based on the chemical formulas and the known products, CO2 and H2O, since it's a combustion process. So first of all, let's lay down what we know. 2.7 liters of propane gas, some volume of O2 gas that we don't know. This is what we're trying to find. And because we're at constant temperature and pressure, we can say that there's some number of moles of propane that this 2.7 liters corresponds to. We could use the temperature and pressure to calculate out this number, but we don't need to, which is why I've just left it as a variable, N. Because of Avogadro's law, we know that the number of moles in this volume of O2 must be 5 times the number of moles in the 2.7 liters of propane in order to ensure complete consumption of the propane, right? The mole ratio is 5 to 1, so the ratio of the moles here must be 5N to N. And now the question is, what is that number of moles and what is the corresponding volume? So again, we could calculate out a number, multiply this number of moles by 5, and then use the ideal gas law kind of in reverse to go backwards to the volume of oxygen gas. But we don't need to do that. All we need to do is think through Avogadro's law. So let's remind ourselves of what Avogadro's law says, particularly the multi-point or multi-state form of Avogadro's law. For any two ideal gases under common conditions of temperature and pressure, V1 divided by N1 equals V2 divided by N2 for the two gases 1 and 2. So V over N for the propane must be equal to V over N for the oxygen gas. And that's exactly what this purple equation says. VO2 divided by 5N moles of O2 equals 2.7 liters divided by N moles of propane. At this point, we can see that the only unknown is actually the volume of O2, since multiplying through by N would divide out N on one side of the equation or the other. So we can solve for the volume of O2 at this point, and it comes out to 13.5 liters, and of course this is simply 5 times the volume of propane used. The volume ratio of O2 to propane is 5 to 1, just like the molar ratio of O2 to propane. That's the beauty of Avogadro's law. It allows us to use volume as a kind of stoichiometric counting unit.